because it was too windy. I wasn't cold. I wasn't cold at all. Water, the wind was so high, the water was coming over into my kayak.
When that happened, we did more than one.
I only walked. So going against the wind to get back to my shore, or get back to my dock, was an adventure. Just water just coming over the top.
Is that actually
going like this?
Is that rip-off goldfish or real goldfish?
That's
Alright.
Looks like rip-off goldfish.
Ready?
the bag. That's the Costco bag. That's fine. Yeah.
All right. If you guys remember, there were Lewis structures that we did where there was multiple ways for us to do the Lewis structure.
You're right.
Okay? For example, here's one of them.
They're the same thing.
We talked about, well, does it matter where I put the double bond? And I said what?
You said it doesn't. You lied.
Okay, I'm going to shatter some things here. Okay? From now on, when you have Lewis structures that you have multiple places that you could put a double bond and you wouldn't know exactly where they were supposed to be, what you need to do is you need to do both structures or all structures. Okay? So from now on, when you come into something that has resonance or something that has multiple places where you could put the double bond, you need to show all of them.
It's the same thing.
I'm going to show you how it's really not.
Oh my soul.
Okay? So if I'm doing SO2 and I do my first SO2 and I choose the double bond here, I must also show the other double bond with an arrow between showing resonance. Now, here's a misconception. Whoops. Okay? A lot of people think that what ends up happening is the molecule oscillates back and forth between the two structures. Okay, that does not happen. Okay? It's not going back and forth between the two structures. That's not what this means when we show resonance this way. Here's what actually happens. Okay? Believe it or not, the bonds of this particular guy are nothing like a double bond and a single bond. What I mean by that is, in this particular guy, all those bonds, none of them are a single bond and none of them are a double bond. So there are a hybrid in between. Okay, for example, when chemists take and look at bond lengths and bond strengths for this guy. Okay, if that were the case, wouldn't they see that a traditional double bond between sulfur and oxygen, wouldn't they see the exact same bond length and bond energy between those two as they would in any other sulfur-oxygen double bond? You would think so, right? Okay? You would think so. But what they actually find is the bond length and bond energy is somewhere in between a double bond and a single bond. And since I have only one double bond and one single bond, what they found is it's actually two 1.5 bonds. Okay, what they find is it's really not a double bond and a single bond, it's two bonds that are hybrids in between. Okay, so what ends up happening actually is you've got two regions and three total bonds. So you have two 1.5 bonds. This. No. Just wait till we get to three regions.
We'll just not do it.
Okay? So the bond length is somewhere in between, is smack dab in between a double and a single bond in this case, and the bond energy is exactly the same, somewhere in between a double bond and a single bond. Okay? This goes into a completely different way of thinking about how these things bond, which when you take a much higher level chemistry class, we will actually talk about something called hybridization, which is the process of forming hybrid bonds when they bond. Right?
When they
So,
This
where does...
class just going to be lies you told us that are
Some of it, yes. Yes, when you guys take higher level classes, they'll be like, hey, remember when you were taught this way? Yeah, it's really not 100% true, but really chemistry is like the class of exceptions. There's thousands of exceptions.
Just like English? Yay!
But anyways, what I'm trying to point out here is, guys, at this level, it makes most sense to explain things how we've explained things, and as you start to build a foundation, it's okay to break some of those things to try, because it helps you understand the big picture, so that when you do get to a deeper level, you have a foundation that you can understand. Okay?
Everything builds off each other. But everything
Alright, here's another one.
nice.
So you have to put both?
So you would have to put both. What would you say the hybrid bond length and bond energies would be? In between, what would you call it? What would you say?
1.5.
This would be also 1.5 because you have two regions. Do you guys understand what I mean when I say here's a region of bond region, here's a bond region. Two bond regions. How many bonds?
3.
3 bonds. So 3 over 2 would be a 1.5. Technically, this bond and this bond are really not a single and a double bond. They're two 1.5 bonds. When you experimentally look at this, their bond length and bond energies are halfway in between a double bond and a single bond. So, if I make you do the Lewis structure of NO3 minus, this is what you'd have to put. All of it. Now, once you do the first one, is the second and third one hard? No, it's more busy work than anything. A little time consuming. Okay? Now if you look at it, I got 3 regions. How many bonds?
4.
So, technically, each bond is actually a hybrid bond.
Wait, you have 4 regions? How's I mean 1, 2, 3.
3 regions,
Why did we
Oh,
do this
4
thing?
bonds. I'm sorry.
4 bonds.
Good night.
Nice, Marty.
Okay, come back.
Okay? So what's actually happening is 1, it's not 3 molecules oscillating back and forth. 2, it's none of these, actually. None of the molecule does not have a double with 2 single bonds. That's not correct either. What is actually correct is what you have is 1 molecule with 3 1.33 bonds. Now, do you see why we don't actually show this in our Lewis structures? Because I don't do this. I don't make you do this. I don't make you go, oh, it's really 3 bonds, but you got to pull out your ruler and find a 1.33 length. Does that make sense? I'd much rather just have you do this and show the resonance than deal with like lengths of bonds.
Well, you
Does that
could
make
just have
sense?
have us put the number on there, like this.
You could, yes. I agree. You could say, well, it's really not a double and a single bond. It's 3 1.33 bonds. Okay? Question on resonance. Any questions? So here's what I'm asking you to do. If you are asked to show resonance or asked to do a Lewis structure of one of these guys where you have multiple places you can put the bonds, then you need to show all of them. Just like you have up there. All right, we're all.
What if you have like that?
This one here. There's only 1 bond there. So there's only 1 bond region.
Oh.
Here, the reason why I have to show all 3 of these is because how do I know if I put the double bond here, here, or here? On that one, there's no other place to put, you can only put that triple bond. Does that make sense?
Yeah.
For example, if I'm doing like this, I don't have to choose where a double bond goes or anything like that, so that's just gonna not have resonance. Does that make sense? Okay? Now, we're going to talk about some exceptions. I'm not going to make you do much with them. You take advanced chemistry, we'll do much more with them. Okay? But I'm going to talk about some exceptions. And we already talked about a few things. We talked about how some Lewis structures, when we did them, we did whatever we had to do to make them stable, right? And that even included some guys giving their electrons to others within a covalently bonded compound. Doesn't that sound like ionic? Okay? Remember that? You never taken some electrons and just popping them to the oxygens to make everything stable? Okay, well believe it or not, a compound is going to do whatever it has to do to become stable. Stable means what?
Low energy.
Low energy. Okay? As long as bonding makes them lower energy than being unbonded, they're going to do it. So there are a few exceptions. Some molecules do not have 8 valence electrons and have an odd number. Here's an example. You might want to put this, write this in here.
That's so weird.
That's a double bond there. I don't know, it looked kind of goofy. So if you look, your oxygen is stable, your 2 oxygens are stable, but what isn't stable? Nitrogen. Now, here's the thing. For this to exist, what has to be true?
The whole thing
They have to be.
Okay.
lower energy than the one.
Yeah. So, in order for this to happen, this whole thing together has to be more stable than what?
Than what they
Than
were.
before.
Than what they were before. Yes. Okay? So, if it's more stable than it being broken apart or whatever it was existing in as before, it's going to do it if they come into contact. Now, we're going to talk in a later chapter where it's not just they're in the same room and there's going to be a reaction. They actually have to collide. They have to collide with enough energy, and they have to collide the right way. Otherwise, they won't react. Okay, but we'll talk about that much later.
What does that make up?
What do you mean, what does that make up?
What is that? What
What is it used for?
Yeah.
I have no idea. I don't know.
I thought it'd be like plants or something.
Yeah, I don't know. I
You
could.
have to specifically collide.
Well, don't get too ahead of ourselves when I'm talking about the 3 things that are required for things to bond. It just means you could have things that are favorable, but if they don't ever come into contact or collide, are they going to react? Does that make sense? I can have something that's extremely favorable to be bonded together, but if they never come in contact, they won't bond. You could have 2 compatible individuals that would be perfect couple together, but if they never meet each other, are they going to get together?
Oh, that's so sad.
That goes all the way back to, does God have a specific individual for you? Or do you get to make the choice? And there's lots of individuals that you could be satisfied and married to.
That's so sad.
God already knows. I agree. God already knows who you will marry.
We have perfectly free will, but God knows.
Yeah.
It's
How does that work, right?
We're not forced to do anything. But God knows.
Are we?
And
Yeah,
knows
right?
He knows what we're
This goes back to the Calvinist Arminian comment.
He controls it.
I got TP'd by Stephen, Andrew, and Peyton Friday night.
No.
What? Why?
They had like a party, and
I didn't even know those 3 hung out
That's so
together.
stupid.
no, well, they hang out for really dumb reasons.
Just to TP people?
No.
You guys get this in?
Yeah.
You guys get this in now? I know this looks goofy because I was having trouble trying to get the dots to be in the right spots.
Oh, yeah.
Okay, but look at this. Does boron have an octet?
I know, but
No.
close.
Could boron even have its own octet unless it were given electrons? Is it even possible for it to have an octet?
No.
No, it has 3 valence electrons. The most it could share and have would be 6. Okay? But, just so happens, this is more stable than boron and fluorine existing by themselves.
So why isn't it just like an ion or whatever? Like the 2 minus to get 2 electrons.
Because charge is always less stable than neutron.
Okay.
Alright, last one. Now, if you want me to do the Lewis structure for this, I will.
Oh,
Oh no, I'm scared.
that sucks.
Ah!
It looks like an octopus.
Yeah, so this would have an octahedral shape.
Exactly.
Which you'll learn that if you take advanced chemistry.
It's got 8. Nope, it's got 12.
I don't know.
Alright, that's what Bill Lewis structure looks like. You're probably thinking, we broke the octet rule! Shame on them!
That sounds like Gingy from Shrek.
What?
I've never seen that
The
one.
gingerbread man or whatever.
Okay?
Oh,
Yes,
yeah.
things can break the octet rule.